Chemical reactions occur all the time, and there are a lot of different ways you can tell whether a chemical reaction has happened or not. Typical ways you can visually see if a chemical reaction has happened are things such as color change, the formation of precipitates or solids within a solution, or the formation of a gas. However, it's these reactions, looking at the formation and the dissolving of a solid, that we're going to focus on in this experiment. Solids can either be formed in a reaction or they can dissolve in a reaction. And this experiment focuses on the ability of solutions to form solids, form precipitates, and the solubility of the solid itself. This experiment focuses on the periodicity of the periodic table, which is inferring different trends within the periodic table itself based on its shape. Are things smaller or larger as you move from left to right? Are they more reactive or less reactive as you move from top to bottom? The periodic table and the shape of that table is in such a way that there are these trends throughout it. Specifically, we'll be looking at the solubility trend within the periodic table for different metal ions. This experiment is one of the first ones where you're seeing a lot of different chemical reactions. The last experiment, you did have the flame test and you saw those and the different colors, but this is an experiment where you're probably thinking or seeing traditional chemical reactions where you're mixing two chemicals together and something happens. So you see a lot of chemical reactions all the time, whether it's burning anything, combustion reactions in an engine or in a fire pit. Almost everything you do when you're cooking something involves chemical reactions, all of them involved in the body in different cells, as well as photosynthesis in plants, and really many, many aspects of making any sort of material. So a number of things can be inferred from chemical reactions. There are visual cues that you can see to determine if a chemical reaction has taken place. So some of these things are a change in color. In this example, it's going from yellow to orange. The formation of a solid. So you mix two liquids together and you get a solid, a precipitate. Or the dissolving of a solid. You have a solid and you add a little bit of some type of liquid and the solid completely goes away. There's the formation of gas. So you'll see bubbles in a reaction, like if you mix baking soda and vinegar. Things that aren't necessarily seen with your eyes, but do indicate a chemical reaction is the change in temperature. You can feel it getting warmer or colder, and the change in pH, or the acid level within a solution. So these are different things that you can measure or see to tell a chemical reaction has taken place. And in this experiment, we're focusing more on this one, the formation of a solid. So every compound, or most all compounds, have a solubility. This is the amount of that solid that can dissolve in water. If you take some table salt itself is a solid, but you can take that and dissolve it in water where it's no longer a solid and it's no longer pure water. It is a solution of salt water. So different compounds have different amounts that they're able to that are able to be dissolved in water. So at a concentration of 0.1 molar, silver nitrate is completely soluble. It's fully dissolved in water. Silver chloride, however, at a concentration of 0.1 does not exist. A lot of the silver chloride will precipitate and form a solid in the solution at the bottom, and the liquid on top is saturated. There is an amount of silver chloride dissolved in that liquid on top that's incredibly small, but it is still there. Silver nitrate can dissolve more than silver chloride. It has a higher solubility. So, as I said, all of these different compounds can dissolve in water to some extent, but it does vary. And this can vary with temperature. Usually increasing the temperature will increase the solubility. And over the years, there have been a lot of these actual numerical values that have been measured, and these are found in solubility tables. And a very extensive one is found on the Wikipedia page for solubility table. This has a lot of different compounds in it, and while not the best source to use as a specific reference for a peer-reviewed journal or report, it is a very good starting point to get a quick reference of what the numerical solubility for a compound would be. So when you're using a solubility table like the one on Wikipedia, it will look something like this one. So there will be a list of the different compounds. It may or may not have the chemical formulas listed. And then it is a table of numbers. And as I had mentioned, the solubility of a compound is dependent on temperature. So there may have a solubility table may have a couple of different values for the same compound because these are the solubility values at different temperatures. The units on a solubility table is how much material is able to be dissolved in water. And most of the time, it should be listed on the table that this is the amount of solid that is able to be dissolved in 100 milliliters of water. So the overall unit for the solubility of copper sulfate at 20 degrees Celsius would be 36.1 grams per 100 milliliters. But having that value, you can also see how much is able to be dissolved in 1 milliliter. So you can convert that from grams per 100 milliliters to grams per milliliter. And in this case, the solubility would 0.361 grams. It can also be converted to the chemistry concentration unit of molarity, which is discussed a little later on in the semester. Now you'll notice not in a solubility table, not every box is filled. This does not mean that a value does not exist. It just means that this table just didn't include it. It might not ever have been measured specifically at that temperature, but it would exist in some form. There are a lot of numbers. So think about every single compound in existence ever at every single temperature. There is no way a table could contain all of those numbers. So many times, especially in older tables, not every compound is included and not every temperature. Some solubility tables may also just list things as soluble or insoluble. This is a quick reference to see just if something can be dissolved, but without any actual values. Pretty much everything, though, does have a value associated with it. So even in this case of silver chloride, it is a very small value. Only 0.0001923 grams are able to be dissolved in 100 milliliters of water. So that is a minuscule amount, but it still does exist. Even in the case of something like lead sulfide, which is incredibly insoluble, there is a number that exists. It has been measured. And so water is able to dissolve a minuscule amount of that, but really barely anything.
Solubility and the solubility value relates to how much of a solid can dissolve in water. In the reaction of lead nitrate with sodium chloride, the solid that would be produced is lead chloride. This, however, is slightly soluble in water. At low concentrations, the precipitate forms and then quickly dissolves as it is below the solubility limit. However, at higher concentrations, the precipitate stays for longer and eventually becomes a fully cloudy solution as the limit has been reached for lead chloride.
Experimentally, you can look at how soluble a compound is based on performing a number of different reactions. And that's what this experiment looks at, is performing a number of different reactions and seeing how soluble something is. So if something is very soluble, it would form a precipitate with very few things. So things like the alkali metals or all nitrate salts, these are very, very incredibly soluble things, and by reacting them with other compounds, no solid forms. They are soluble. But if something is very insoluble, such as lead or barium or carbonate compounds, if you have a solution of one of these compounds and mix them with something else, they will form a precipitate, and you will see this. So in this picture example right here, these two combinations are soluble, and these combinations are insoluble. The compounds formed on this side have a very low solubility, where the compounds involved on the other side have a very high solubility. The same solubility and reactivity, though, have an inverse relationship. So something that is very soluble means it dissolved. It did not form a precipitate with anything. It stayed dissolved in water, so it did not react. It was very soluble, but not reactive. Likewise, if you have a compound like silver ions are very, very reactive, and they form a precipitate and come out of solution with almost anything. Silver ions are very reactive, but very insoluble. So whatever is soluble is typically non-reactive, and whatever is insoluble is more reactive. This experiment is a qualitative experiment. You are just looking at overall patterns. You're not focusing on the specific values and amounts, but the overall trend, and the trend within the periodic table. So how you'll look at this and rank the solubility and rank the reactivity is by looking at how many reactions something occurs, or something that occur. So in this example, in these two pictures right here. You have one solution. It formed a reaction and formed a precipitate with 3 separate things. So in this, this reactant, metal ion A, caused 3 reactions and precipitated 3 times. Metal ion B, in reacting with the same solutions, produced 5 different precipitates. It reacted 5 times where this compound only reacted 3. That means that compound B is more reactive. There are more reactions than in compound A, but compound A, the metal ion A, is more soluble. It's able to dissolve in more environments than the second one. So one thing that's very important to know in this reaction is, or in this experiment, is the fact that you're looking at metal ions. So these metal ions are different from the metals themselves. So in the case of something like sodium chloride, you are looking at the reaction and precipitation patterns and solubility of sodium chloride, the sodium ion and the chloride ion. Sodium ion is in table salt. It dissolves in water. It's very inert. It doesn't really react with anything. You eat it. Sodium metal, the pure metal from the periodic table, is an incredibly reactive metal that will explode in water. They are not the same thing. When you are recording something or when you are writing something in a report or really anywhere, you need to indicate whether it's an ion, whether it's a metal, or something like that, because Na is completely different than Na+. In these reactions, in this experiment, you're focusing on the metal ions themselves. So when writing them out, you can either include the different charges, or if you're writing out the words, you can write out ion after it to indicate that you are working with the ion compounds and not the direct elements themselves.
Overall, this experiment focuses on the trend of solubility as it relates to position on the periodic table. The periodic table is arranged in such a way where different elements with similar properties are grouped in the same column and the same row or period. As you're going through this experiment, you're looking at the number of times an ion reacts and where is it on the periodic table. You're looking to see, as you move from left to right on the periodic table, do compounds become more soluble or less soluble? As you move from top to bottom on the periodic table, do things become more reactive or less reactive? There are a lot of different trends that are associated with the position on the periodic table. And this experiment focuses on the joint trend of solubility and reactivity.
This experiment looks at the trends associated with solubility and reactivity of the metal ions. And you're looking at it based on the shape of the periodic table. Something like vanadium, or the vanadium ion. Is that reactive? Is it soluble? Is the cesium ion reactive? Is it soluble? Lead ion, reactive, soluble? If you look at the periodic table and based on their position, you could infer kind of a general sense of, is one thing more reactive than the other? So the periodic table is shaped and grouped in such a way that like compounds or elements with similar properties are in the same group. So you see the periodic table is in this sort of a shape. And again, like elements with like properties are in the same group or the same columns. And there are the different sections of the periodic table. So I have the alkali metals, the alkaline earth metals, transition metals, the rare earth metals down here, and then noble gases, halogens, post-transition metals, these sorts of things. And where things are on the periodic table plays an important role in inferring what types of reactions and how the different properties of those elements. So some of the other periodic trends can be seen here. So atomic radius. In the lower left has a high atomic radius, and in the upper right has a small atomic radius. The overall trend goes from large to small as you move up and to the right. Electronegativity has the opposite trend. Things that are in the upper right are very electronegative, while things in the lower left are very not electronegative. The trend moves from upper right to lower left. Ionization energy is similar. Melting point seems to have, in the transition metals have a high melting point versus lower melting points towards the end. And it's these types of trends in the periodic table that this experiment is looking at, but not these direct measurements, but solubility. As you move from left to right on the periodic table, do the metal ions become more soluble or less soluble? Do they become more reactive or less reactive? Also, as you're moving from top to bottom, do things become more soluble or less soluble, or more reactive or less reactive? And that's what this experiment is looking at, and that's what you're inferring from all of the different precipitation patterns.
In the lab, you're going to be performing a number of different reactions and a number of different combinations to look at the different observations that indicate a chemical reaction has occurred, and also looking at the trends of these reactions to determine what is the trend of reactivity and solubility based solely on where a metal ion appears within the periodic table. The first part of the experiment is really just focusing on observations themselves. You're looking at a number of different chemical reactions performed in small test tubes and getting a sense of what types of observations you can see that indicate a chemical reaction has occurred. You're going to be looking at 4 or 5 different reactions in small test tubes and determining, did a reaction occur? Look at the observations, look at the physical things you can see or feel. Temperature change is something that you could feel in the test tube. Is it getting hot? Is it getting cold? Things like that. So this would be the first part of the experiment.
In the first part of the experiment, you're mixing chemicals together in specific quantities. You're going to be looking on the supplementary information at what different experiments you're going to be performing in small test tubes. By doing these experiments and mixing these chemicals together, you're going to get a sense of what different types of observations indicate that a chemical reaction happens. In small test tubes, you're going to add a few drops or small amounts of different mixtures and different chemicals and recording what are the observations that you see that happen in these different chemical reactions. You'll see a number of different chemical reactions that happen as you continue to mix things together. Some things will cause color changes, others will cause precipitates to form, some may form gas formation, and these sorts of things. So you're looking what happens when you mix things together and what are the visual observations that you can tell that a chemical reaction has occurred.
The bulk of the experiment looks at performing a number of different reactions in a 96 well plate. And while there are solubility rules, things like all alkali metals are soluble, all nitrates are soluble, many silver compounds are insoluble, these are relatively generic and they just kind of give some specifics here or there. What this experiment does is by looking at the trend of solubility and reactivity based on the periodic table, it can define an overall trend of these solubilities of different metal ions. So you're going to be making an array of a number of different metal ion salts, different metal ion nitrates, which are all soluble, and alkali metal salts. So those are all soluble as well, but the combinations may not be. And in this, you're not looking at exactly what the solid compound is, that's the product. You're just looking at the pattern. How many times does a particular compound form a precipitate? So in the reaction itself, you're setting this up in your 96 well plate. There are 12 different metal ions, metal nitrate salts, all of these are soluble, as well as some different alkali metal precipitating agents, and all of these are soluble. The one exception will be the mercury, which you won't be working with directly in the lab, but the observations are provided for you. So in the experiment, you're really making a full 96 well plate, all of these different combinations, and you're recording what are your observations throughout this experiment and determining which ones of these different metal ions precipitate more and are more reactive and therefore less soluble, and which ones barely precipitate at all or not at all, meaning they're very soluble and not very reactive. That's the inverse relationship. Is if something is reactive, then it is not very soluble. If something is very soluble, then it's not very reactive.
The bulk of the experiment involves making an array of a number of different reactions in a 96 well plate. You're going to be reacting 12 different solutions with 7 other different solutions for a combination of 72 different reactions or 72 different combinations of chemicals. There are 12 metal nitrate salts and a number of sodium precipitating agents. And what you'll be doing is reacting these and combining them to see which metal ions will precipitate with different precipitating agents or different anions. So what you'll end up doing is taking one of the metal nitrate solutions and adding 2 or 3 drops in each of the wells going all the way across the 96 well plate. You'll do this for all of your different metal ion solutions. There are 12 metal ion solutions in total. However, you will not be given the mercury nitrate solution for safety reasons. The observations of the mercury nitrate combinations will be provided to you, and in the video you can see what they will actually look like. So once you have all of your metal nitrate solutions across in each one of the rows, then you can start out with the different precipitating reagents, or vice versa. Again, these are now going all the way down the entire well plate. And there are 7 different precipitating agents that you're going to be using. So now, just on our small array of aluminum, barium, and silver nitrate salts, reacting with sodium nitrate, sodium hydroxide, and potassium chromate, you can see that the aluminum nitrate along the top did not precipitate with anything. However, both the barium nitrate in the second row and the silver nitrate in the third row did react with two different materials. From this, we can see that the aluminum nitrate is less reactive and therefore more soluble than the other two, either barium or silver nitrate. You're going to be looking at all 12 of these different metal nitrate salts, as well as an unknown metal nitrate salt. For the unknown, you will be looking at what is the pattern of your unknown and comparing that to what you actually got. In the end, the 96 well plate would look something like this, where you have a number of different precipitates in multiple different wells. Some have different colors, others do not. Many of them are white precipitates, so you may want to have this on a black background so you can see the precipitates more clearly. In the lab report, you're going to be comparing across the rows and periods and up and down the columns on the periodic table and looking to see which metal ions precipitate with more components, and that would be a more reactive material. You'll also be comparing an unknown. For reacting the unknown, you'll take it and use it just like one of the other metal nitrate salts. You'll react the unknown with all of the precipitating agents just in a different row and try to match its pattern. See which unknown or which one of the known metal nitrates has the same pattern as your unknown. And that's how you can determine the identity of the unknown salt. This is the bulk of the experiment, and there will only be so many bottles in the room, so much of your time may be spent trying to find where those end up. But overall, you should be getting a full array of different compounds and different reactions. If you are unsure if a reaction has happened in this 96 well plate, you can always repeat the reaction in a larger test tube, so that way you can see the observations more clearly and make an informed observation about the combination.
So you saw how you're going to be mixing all of these different things together in that 96 well plate. You're going to be taking things like the aluminum nitrate and putting 2 or 3 drops in every well all the way across. Barium nitrate, next row down in every well all the way across. The sodium nitrate, the precipitating agent version, every well all the way down, 2 or 3 drops. The sodium chloride, next column over, every well, 2 or 3 drops. And you'll end up with something like this that has the pattern of which combinations of aluminum nitrate form a precipitate, which combinations of barium nitrate form a precipitate. And you're counting these up to see which compounds are very reactive and form many precipitates. So this is a very insoluble compound right here. And which ones form very few or no precipitates, meaning that it is a very soluble compound, like this one here. As I had mentioned, the mercury nitrate itself is not something that you'll be handling in lab due to the toxicity. So the observations of what actually occurs is listed in the report itself, but also this is kind of a picture representation of what those different combinations actually look like if they were to have been performed. The last part of the experiment is just a continuation of that. You're using an unknown ion, and you're going to be reacting that unknown with all of the different precipitating agents. You're just going to treat that like another metal nitrate salt. And by doing so, you're going to qualitatively determine what this unknown ion is, or what are the possibilities. So by looking at your known patterns, looking at what is the pattern that barium nitrates precipitates with, and does that match the pattern of your unknown? There are only so many possibilities of what the unknown is, because some of them do kind of overlap in their actual pattern. So there are only a select number of possibilities for the unknown ion. You're going to be looking at what is the pattern of your unknown ion and compare that to what you had just done in the lab. Which one of those known metal ions matches your pattern? And that's how you would be determining what is the identity of your unknown ion. Now, since this whole experiment is looking at solubility, a very good resource for what the actual solubility is are solubility tables. And there is a very good one on Wikipedia that could be used as kind of a jumping off point for determining some of the values. Wikipedia is not a great direct source to cite in papers or reports, but it is a very good place to look to get a quick reference of what the numbers are. And typically, the numbers are cited in a more legitimate source in some of the references. Your lab manual also has a list of solubility values for a number of different compounds that you'd be working with in this lab and throughout the course. And these values directly from your lab manual can be used as a reference, as these values were specifically obtained from direct references, CRC manuals, and legitimate solubility papers and things. So when you're looking at these solubility tables, either on Wikipedia or in the lab manual, you'll want to be looking at what are the units. Keep in mind that these units are not simply grams per milliliters or molarity or things, but it's grams per 100 milliliters. That's the standard solubility unit in these solubility tables. But what you're trying to get at is what these solubility values actually mean. It's a number. All of these compounds have a solubility number. What does that mean? And think about what that would mean in terms of precipitation. And especially when looking at the Wikipedia table, because that has a lot more temperatures for the solubility, look to see how does the temperature actually affect the solubility? Does it go up or down with temperature in general? So these are the things you're going to be looking at in the report for some of these questions. You're determining the overall trend of solubility of metal ions, and then you'll also be using solubility tables to answer some of the questions about what these numbers actually mean and what does it mean that something is soluble or insoluble.
Overall, this experiment is looking at the solubility and reactivity of metal ions and how it relates to their position on the periodic table. Moving from left to right, as well as from top to bottom on the periodic table, can show different trends from electronegativity, ionic size, atomic size, density. There are a lot of different things that can be inferred based solely on where an element is on the periodic table. And this experiment focuses on solubility and reactivity.